Welcome to Introduction to Fluid Mechanics. Today we are starting a new chapter on controlled volume analysis of fluid systems. In the previous chapter, number 2, we dealt with static fluids, and we define a static fluid as a fluid system that cannot sustain shear stress forces between the fluid elements. And the only force that existed between the fluid elements themselves was the pressure force, which was compressive and perpendicular. But now as our fluid starts moving, the fluid elements will start rubbing against each other, and friction will exist. But that's one point. The other point is that as the fluid starts moving, it has a velocity, and when it has a velocity and has a mass, it would have momentum, and at the same time it would have energy. So the type of analysis that we now want to do is different than what we have done before. For us to be able to understand these moving systems, we want now to consider their momentum conservation, we want to consider their mass conservation, and we want to consider their energy conservation. So these are the basic principles that we want to cover in this chapter number 3, which is the basic principles that we believe to be true, and there's sufficient evidence that these principles are true, which is the conservation of mass. Mass is not destroyed nor created. Energy is not destroyed or created, but you can transform it from one form to another. And linear momentum conservation, that is, you need a force to change the direction or the velocity of an object of mass m, or force equal mass times acceleration. The objective of this course, so we know all these principles, they aren't new to us, they're familiar principles, but what we will be doing over the course of the coming lectures is to be able to mathematically express and write these 3 principles for a flowing system. And for that, we will revert to the controlled volume concept that we have seen in thermodynamics, which divides or somehow defines a system as a set of inputs and inlets and outlets and some other boundaries. So a controlled volume is a system that has boundaries, and mass crosses those boundaries, and with the crossing of the boundaries, also that mass carries with it momentum and energy, so energy crosses that boundary. So that's what we have seen in thermodynamics, is that energy crossed the boundaries between a pump and a boiler and so on. So now let's consider this jet engine. It's welded to this wing right over here, so there's a weld. And now if I try to consider, I want to know how much thrust force this engine produces, then thrust. So when I'm talking about force, I might consider doing a force analysis on this, which means, because now air is moving, that I want to do sigma F equal ma, which is a linear momentum analysis. And what do we do that linear momentum analysis on? Do we do it on the moving air? So now, to simplify things, it is much easier to do it on a controlled volume. So this is the inlet. This line represents the inlet to the jet engine. So flow of air comes through the jet engine and leaves from the other end, which is the outlet. So that's an outlet of my controlled volume. This is an inlet, and then I complete my controlled volume to be a closed system. And you see, when I did that, I cut through this weld right over here, and right at the bottom, I'm not cutting through anything. So if I were to simplify this picture, now that you see what the concept is, we have an engine, and that engine is suspended through a weld to the wing, and my control volume has cut through that weld and cut through the outlet and cut through the inlet. So this is my control volume, and this is my jet engine right over here. And what we will learn in this chapter is how to write the conservation of energy and mass and momentum for a control volume like this. How can we express that mass is conserved in here? So right, there is m dot in, that's mass flow rate that comes in, and m dot out. And we want to relate the mass flow to the moving fluid, that is, to the velocity of the fluid. So that's the idea. So now let's start with a simple example with a demonstration. And for that, I'm using this YouTube video. The reason why I picked this video is that they use an advanced flow visualization technique called the Schlieren visualization, which lets you see variations in the density of air, small, minute variations in the density of the air using a set of lenses and lighting and mirrors. So let's watch this. What you will have here, right? So this is the field of view which a Schlieren system sees. So when I play this system, you will see that the natural air. Oops. Okay, never mind. Let's watch this video. So you have a ping pong ball suspended in an airstream. And you can do this actually at home, and we can see the white stuff is the variations in the density of the air due to its velocity. So we can tilt the hair dryer and the ping pong ball stays suspended, and so on and so forth. Okay, so what we saw is the Schlieren effect allows us to see the variations in density in the fluid through the light effect, through the index of refraction variation. And what we've just seen was a hairdryer that ejects a stream of air, and ping pong ball got suspended. So now what this tells us, once the air, so what we can conclude from this picture, what we can observe in this picture is that there was an airstream. So there was an airstream, and there was that airstream had a velocity. And that velocity was able to create a force. And how did we observe that force? Is by seeing that this ping pong ball is being suspended in the airstream. We're looking at the same thing except in two different lightings. That's what you would see with your eye before, and here's what you would see under a Schlieren system visualization. So we're seeing the airstream. That's what's nice about this experiment. So we had two, if you look at two snapshots of the demonstration that we have just shown a minute ago, you'll see the case where you have the ball is vertically suspended, but also you could see the case where the ball is, the airstream is tilted. And let's see what we can notice over here. The first thing that we can notice in the case of a vertically suspended ball, the airstream is going vertical, is that you see if I were to draw a control volume over here around the ball, you will see that the width of the airstream at the inlet is actually less than what it is at the outlet. So that's our first observation. We see that the air deflects around the ball, which we'd expect because the ball takes space, so we need space for the ball and the airstream at the same time. And what you'd see here, you want to think of the bright light to be faster fluid, and the darker, shadower region right here to be slower fluid. But what you'd notice is that there is sort of symmetric flow left and right of the bowl. But the important thing to notice also is that the width of the airstream that comes into the control volume is actually smaller than what leaves, and this has implications on the force generated on the bowl. So now we can take the other case where we had the airstream going at an angle while the ball is suspended with its mg pointing downward. So that's the downward g gravitational direction. So there is an angle between the airstream and the gravity force on the ball. And what you will see is a non-symmetric one. Is, let's look at this. You'll still notice that the incoming jet is still thinner than what you have for the outlet flow, airflow. And for the outlet airflow, you'd expect, at least what we see here, is we have faster flow in this region and slower flow in this region over here. So we have some sort of asymmetry that compared to what we have seen in this case, where we saw a symmetric flow left and right along the symmetry line. While here, that asymmetry we'd expect is associated with the inclination angle between the gravitational vector and the airstream. So these are the type of things we will be considering in our study, is that when we take control volumes, it will help us understand what is happening, what is happening in the flow field. So now we're mentioning a flow field, so let's come to that in a second. And what are the forces generated in that flow field? So now we came up with the word flow field, which means that the air, we have a field of airflow, and there is at each point x, y, and z. For instance, you take this is my coordinate system, x and y, and perhaps z into the page. At this particular point, I have the velocity of the air moving in this direction. At this point, it was probably moving in this direction. So I have a velocity field, a flow field, and a velocity field that varies in space in x, y, and z. The velocity itself varies in magnitude, and it varies in direction with the location in space. There are more videos that you can watch right here that talk about this ping pong ball. But now let's make some observations. One is that the air has a velocity, and the air at any point around the ball has a velocity which we will describe it as the derivative of the positional vector of the air particle relative to time. And here we show two cuts in this velocity field. So at the inlet, I am showing you the velocity that comes into the control volume, and you'll see that it's uniform and uniform in magnitude, and it's uniform in direction. It's all pointing upwards. And if I take a certain distance far away from the ball, above the ball, I will notice what I've noticed in the previous video, also in the snapshots, is that we had a region, a darker region. We had a brighter region here, so a brighter region here, which was faster flow, and we had a darker region right here. And that's what we noticed. You'll see that the length of the vector here is less than what it is towards the center line, is less than what you have at that region. And I can do this. I've done it for only the before, upstream of the ball. That's what we call upstream. because that's where the flow is coming from, and downstream that's where the flow is heading. It's heading down to the downstream. So that is downstream. So I've shown it at upstream and downstream. I can take any other cut and show you what the velocity is going to be. But what this tells us is at any point x, y, z, and at any point in time, there is the air particle has a velocity v, which has three components. One in the x, so I think we need to define our coordinate system. This is x right here. This would be y, and z is into the page. And the velocity along the air velocity along the x direction, we're going to call it u, and we're going to stick with that. And y is we're going to call it v, and in the z direction we're going to call the velocity w. So the three components of velocity along the x, y, the orthogonal velocities are u, v, and w. So we have a velocity field, and what we will notice also that we will have a pressure field and also a shear stress field, but more on this in a second. So we will have a pressure field and we will have a friction field or shear stress field. And the other force that we see, notice here, is that the weight of the ball or the weight of the airfield. So now let's go back to our, so that's the flow field. That's what we have over here. Now let's talk about the control volume itself. So what I've drawn here in red is my control volume, and that's what's going to help me do the analyses that I want to do later on. That is, I want to relate the velocities of the air that comes into the control volume and leaves the control volume to how much weight that the ball has. So that's what we are going to do next. So a control volume analysis has it's very powerful because I don't really need to know what's happening inside my control volume. It's a black box analysis. All I need to know is what's going into my control volume and what is leaving from my control volume. And by balancing momentum and mass and energy and so on, I can tell you what should the weight of the ball be. So this is one case of a controlled volume. But for that type of controlled volume, I need to know something. I need to know to have a well-defined conditions at the boundaries of my control volume. That is in terms of what is the pressure distribution, what is the velocity distribution, and what is the friction distribution over there. But the take-home message from this slide is that we have a velocity field as a function of x, y, z, and t, and the velocity field is three components, and we have a pressure field. So this is one type of control volume. Now, the choice of control volume is very important. Let me give you another example of a control volume for the same problem. And now I pick my control volume now to be just right at the surface of the ball. And when I do that, the type of analysis that I will do is going to be completely different than the previous example where I have picked my control volume to be far, not to touch the ball, and to be sufficiently far away from the solid object here. But now that I have the control volume hugging the surface of the ball, my analysis is going to be completely different, because if I look at what forces are acting on the surface of the ball, one is definitely there is going to be pressure, but also at the same time we're going to have friction, which is parallel. So I'm going to get a shear stress and a normal stress, which I'm going to call pressure, and here I have a shear. And the pressure around the ball is going to be different depending on its position, angular position, as well as the shear stress. But the net of that, if I integrate over the whole surface of the ball, I'm going to get the force due to the shear stress, and I'm going to get the force due to the pressure field. Now that we are talking about about this particular control volume, I want to use it as an entry point to introduce the no-slip condition. And if I now look at any fluid particle that's touching the surface of the ball, and I try to measure its velocity, I'm going to notice that it's 0. And this has been done through empirical experiments. So there's a lot of empirical evidence and lots of experiments that show that a fluid particle that is directly in touch with a solid object, such as the surface of this ping pong ball, is going to have 0 velocity. And that's what we call the no-slip condition. And when we have an impermeable solid object, that is, the flow can't go in through the solid object, then the velocity of the fluid particle that's right at the boundary of the solid object is going to be the same velocity as the solid object. So keep this in mind, the no-slip condition, because we will need it later on. Okay, so these are two types of control volume that we have just seen, and the questions that I might be interested in answering would be, for instance, how fast, so here let's just go back to those two examples. How fast should my airstream be, right, to suspend the ball? Or one other question could be, what is the largest ball that this airstream can suspend? Or in this particular case, in the inclined case, what is the largest ball? Is it the same in both cases? Would I be able to, for that same airstream, would I be able to suspend the same ball size and same ball mass in the two cases with the same airstream? And for us to be able to answer questions like this, we want to be able to do force balances. And why is there a force in the first place on the ball? Well, primarily because air comes out of the hair dryer, and that air carries momentum with it, and as it hits the ball, we've seen that it generates shear stress and pressure stress, which impart part of that momentum onto the ball, and then the air leaves with less momentum on average after it leaves. So because the reason why we need to do control volume analysis is that it helps us answer questions like this. And control volume analysis, as we said, is a black box analysis. All I need to know is what's happening at the boundaries, and then that will tell me a lot about what's happening inside the control volume. So all I need to know with my control volume analysis is to know what's happening at the outlet here and what's happening at the inlet. And this is what's happening at the inlet. You have a very fast flow, which is concentrated and thin, and then here you have sort of a slow flow and a slightly faster flow in this region. So we will come to this later on. But as we said, the reason why there is a force generated is because the air has momentum. It has lost some of its momentum to the ball, and it's left with less momentum. But that air also has a mass, and this is continual. It's not the same air that comes in and then, every second and every moment I have a new charge, a fresh mass of air that comes in and leaves. So that is the first order of analysis. Is I want to know how much of that air is coming into the boundary of my control volume. If I'm able to quantify that, then I could move on to more complex analyses, such as what is the maximum weight of the ball that I can suspend in this jet stream. So our first order of business is to try and understand how much mass is being carried, is entering my control volume right over here. So for that, let's go to the beach, and let's do a simple experiment on the beach, which is to scoop sand. So you're on the beach, you have a cup or you have a shovel, and you're scooping sand from the beach into the bucket. And the question is, can you fill the bucket in 1 minute? Are you going to fill the bucket in 1 minute or in 10 minutes? It depends on how fast you scoop and how much mass flow rate goes from the beach sand into the bucket. Okay, so here is our scooping experiment. We have a cup over here and we have a pile of sand. And now this cup has an opening of area A, and the orientation is given by the normal vector n, and we're moving the cup in the direction of the normal vector n towards the pile of sand. And now imagine that I move a certain distance delta x right here in the direction of motion. So the amount of sand that is going, so I move that cup, cut into the sand pile, the amount of, and this is the distance delta x, the amount of sand that is going to get into my cup or cross through this surface area A is just this, the volume will be delta x times the area. So that's how much volume of sand is going to get through the area A. So now how much volume per unit time I'm going to get depends not only on the distance that I move my cup into the sand, I dig the cup into the sand, but on how fast I dig it. So it is the this volume per unit time, and the volume is A delta x. So the area of the cup is constant, but how fast I scoop, delta x over t, which is actually the velocity at which I'm moving, delta x over t. So the volumetric flow rate would actually be the area multiplied by the velocity v. But which velocity v? It's actually the velocity in the direction of the normal vector to the area. So you could now think of the theoretical case where this is my pile of sand here, right, as shown. But now instead of having my, and this is the cup's open area, but now imagine that I'm moving the cup parallel to the pile of sand in this direction. This is my V. Naturally, you're not going to get any sand into the cup because nothing is crossing through that particular area. They're moving parallel. So really the velocity I'm talking about over here is the velocity perpendicular to the area A, or parallel to the normal vector n. And when I multiply the area by the velocity, I could do, I can mathematically describe this, that perpendicular velocity, as a dot product of the velocity with the normal unit vector n. And when you do a dot product, it's really the, you multiply by a cosine theta between the vector n and the directional vector v. So that is our volumetric flow rate. But now imagine I want to get mass. Mass is just the density times volume, so that gives me a mass. And if I want a mass flow rate, I just divide by time. So it's the same story, and so all you need to do is just multiply by the density. Multiply the volumetric flow rate by density, you get the mass flow rate, and this would be the relationship we'll be using in this course for the mass flow rate. Now let's look at other cases. Imagine now other theoretical cases. Imagine now that the pile of sand is going towards you at a velocity v, and you're going to, so at a velocity v, and you're also scooping in the direction of the pile of sand at the velocity v. The amount of sand that gets into the rate at which sand gets into your cup is actually 2v. So this is the case where if you have a river and you have a flow in the river of velocity v, and you have a cup, and you try to, if you let it sit there, just sit there, it will fill at a rate of velocity v. That's how much mass flow rate is going to get into your cup. But imagine now that you're scooping your cup at a velocity v upwards, or some other velocity, then it's the relative velocity between them. And since they're in opposite direction, that will sum up. Now, the last point I want to make over here is that this cup is just it's just to help our imagination. But now imagine the whole story without the cup. All you care about is this area. So really, you'll see in this formula right over here, there is no cup. There is only a cross-sectional area where fluxes go through, and we have the normal velocity of that cross-sectional area. So this is part of the boundary. We've completed the boundaries of our boundary of our control volume. And for this part of this portion of the boundary of our control volume, which has an area A and normal vector n, that's all that matters for how much mass flow rate is going through this particular boundary. So keep that in mind. So now relative velocity. So now the next thing we went into is when I have the fluid itself is moving, so the pile of sand is moving or the river is moving, and my area A, which is part of my boundary itself, is moving. Then I get what's called the relative velocity. And now relative velocity is actually very important. And the relative velocity is just the difference in velocity between the fluid and the boundary. So the boundary represented by the area A. So we still have the dot product, and now we just want to make sure it's the relative velocity between the two. And the relative velocity is the vectorial velocity. So this comes into manifestation in aerodynamics quite a bit. For instance, if you fly from Paris to New York, when you head west, it's actually going to take you longer than to fly east, such as from New York to Paris. And the reason is because the flow itself, the air in which the airplane is suspended, has a direction of motion. So we will explain this a little bit more in the coming slides. But I want to point you to this link over here, which tells, or you can just Google it, maybe you can click on the link. British Airways has set a record crossing of the Atlantic in less than 5 hours. So that was on February 9, 2020. So they keep breaking these records. And the reason is they had a tailwind. So let's talk about that in a second. But there is another example, which is if you take a helicopter, ride in a helicopter on a quiet day, there's no wind, you ride up 1 kilometer above the surface of the earth, the earth is rotating, and you wait there for an hour. Would you land in a different place, or would you land in the same place? Like, would you land in a different city because of the rotation of the earth? So that's a thought question that I would like you to look into. Okay, so let's look at the relative wind speed. Remember we had the scooping with a cup from the river. The river had a velocity, the cup had a velocity, and then we had the third velocity, which is the difference between them, which we call the relative velocity. So for an airplane flying from point A to point B, the velocity of the airplane, which you can consider as our cup, is just, we're going to call it the ground velocity, which is what you measure with a GPS speed. So if you're sitting on an airplane and you look at the monitor, that's the ground velocity that you get over there. And which is the velocity observed. This is the velocity of the airplane, or the control volume, or that particular area we're interested in, the area of the engine, seen by a fixed observer on the ground. But then let's say that same observer on the ground looks at the clouds that are around the airplane. They will notice that the clouds are also moving at a velocity. They could be moving in the same direction as the airplane, or the cloud is moving in an opposite direction of the airplane, or in any other direction. So that's the atmospheric wind speed. Let's call it VA, and that's typically measured by a ground weather station. And now, if I am sitting on the airplane, the engine and the other instruments on the airplane, such as the speed sensor, all they care about is actually, they don't care about the ground speed only, or the atmospheric airspeed only. They care about the relative velocity, because that's the velocity responsible for the mass flow rate going into the engines of the airplane. So that, as well as the mass flow rate flowing over the wings, and it's what controls the amount of force that the wing generates. So it's an important velocity that we have to clarify a little bit more. So that's the relative velocity. So it's the relative velocity between the air and the airplane. And the relative velocity is the velocity seen, the velocity of the wind seen by someone sitting on the airplane. And really the way you measure this is you actually have someone or something sit on the airplane and measure the air velocity. So you have what's called this disputer tube, and it's a velocity measurement device that actually measures the difference between VG and VA, which is the relative velocity, directly gives it to you. And it looks like this. It's something that sticks out of the body of the aircraft and measures this relative velocity. And this is the relative velocity that we have seen before, that's responsible for the mass flow rate. And that mass flow rate, as it flows over the airplane, carries with it momentum and carries with it energy. So all the energetics, all the momentum conservation calculations will have to depend on this relative velocity. Very well. And this is a slide from my aerodynamics course. So the relative velocity is what you actually use in all your aerodynamic calculations, such as the lift calculation and drag and so on. So again, it's because of the mass fluxes, and as we have seen, the mass flux depends on the relative velocity, or the mass flow rate depends on the relative velocity in the previous slide, v relative dot NDA. And also the forces will depend on that. We'll come to this slide later on to explain what it is. So let's look at the relative velocity in a more practical fashion and application. So if you look at the monitor, you can see right. So I think this answers the question: is when you ride up in a helicopter, are you going to land and you stay an hour suspended in the air, or are you going to land in the same place or in a different place? So I'll let you think about that, and I'm gonna skip over this and let you think about it. So we're still talking about the relative velocity, and you're sitting on an airplane, and you'll see that there's the ground speed, which is the speed of the airplane seen by an observer sitting on the ground, which is the same what the GPS system does. It gives you, if you have a GPS system when you're riding on an airplane, you're going to get the same speed, that what's called the ground speed. But also on the monitor you have what's called tailwind. Sometimes it says tailwind, sometimes it says headwind. And that's really, so this is the VG, which we have seen 2 slides ago, and this is the VA as measured by a weather station, and the relative velocity is the difference between those two. And so let's look at those two cases, a tailwind and a headwind. So here's my VG, the ground velocity, and this is the atmospheric air. If you're moving in the same direction, then they subtract. But now if you have headwind, the relative velocity would be the summation of the magnitudes of those two of the Vg and Va, and that's the reason why. So that's the reason why you get a difference in time and ground speed, flying east or flying west. The reason is because you have a jet stream. So if you're heading towards the east, you're riding on this jet stream and you don't have to work as hard. But if you're heading west, you have to move relative to the ground, but also to overcome the speed, the jet stream velocity. But why? You may ask why. Well, so let's take it from the point of view of the engine. So let's say the engine has to produce a certain amount of thrust force, and that thrust force depends on the mass flow rate that goes through the engine. And the mass flow, so let's say, and the mass flow rate that goes through the engine is just depends on the density, the relative velocity, and the area of the opening area of the engine. So with the area and the density being constant, the relative velocity is what I care about. And let's say for me, my engine needs to run at a certain mass flow rate, which means it needs to run at a certain certain v relative that is the same whether you're heading east. V relative is the same. Let's say 500 kilometers per hour, whether you're heading east or whether you're heading west. Same v relative. But if I have a difference and then what you now can see is that the v relative, as you can write it as the VA minus VG. So if I'm only looking at VG is my ground velocity, my ground velocity will be VR minus VA. And depending on whether, so my ground velocity, so since V relative is the same, it has to be the same because it's set by the engines and by the wings and by the aerodynamics. It has to be the same whether heading east or whether heading west. It must be then my ground velocity that varies depending on, because VG will be VA minus V relative. So since VA is variable and V relative is constant, then my ground velocity is going to vary, which means for an observer sitting on the ground, they will see, so an observer sitting on the ground, when the airplane is heading east, they will see that the airplane is going at 800 kilometers per hour, while they will see the same airplane moving, when it's moving west, it's only moving at maybe 700 or 600 kilometers per hour. So let's take this example into more detail. And first, let's just let's look at the implications of landing in headwind and landing in tailwind. So here's landing in headwind, and you can watch the YouTube video over here. And look at the ground velocity of the aircraft when it lands. So let's watch that. And then we will look at the ground. We will watch another video of the ground velocity when we're landing in tailwind. So let's see. So pay attention to once the aircraft lands, pay attention to its velocity on the runway. It's landing in headwind. You notice that the airplane lands with a very small ground speed, and it only takes a short part of the runway to come to a complete stop, just because it's in headwind. Okay. Okay, so here we have landing in a tailwind. So you see the airplane on the runway is still going full speed. Its ground speed is very high that it came at. Okay, so let's analyze those two. So let's analyze those two cases. We see that the ground speed for a tailwind landing is actually much higher than the ground speed in a headwind landing. So let's put some numbers on those equations. So now I have, let's say the V relative has to be, that's set by the engine. Let's say it's set by the engine of 300 kilometers per hour. And that means it's the negative means it's the velocity seen by someone sitting on the velocity of the wind seen by someone sitting on the airplane. So someone sitting on the airplane will see the wind coming towards them, which is towards the left. That's why it's in the I direction, in the negative I direction. And the ground, then I have, that's the ground speed of the aircraft, and that's the VA. So the V relative is the atmospheric wind. So let's say I am in a 50 kilometer per hour headwind. So what should my ground speed be? My V relative is minus 300, and the headwind is to the left, so that's why it's minus 50. So my ground speed is going to be actually 250. That's how you get a minus 300 because of the minus sign. So when you're landing in headwind, your ground speed is 250. Let's look at the same case. Well, the engine sets the relative velocity. Let's say, just to simplify it, the aerodynamics have to set the relative velocity to be a certain value that we have to stick with. So let's say 300. But now I would be landing in tailwind, so I'm landing in a wind that is going to the right. That's why it's plus x in the positive x direction at 50. So what do you need for VG to get a minus 300? So this has to be really 350 to get the 300, a plus 350. So you'll see the ground speed in the first case was 250 in the headwind, while in the tailwind it was 350. That's a significant difference, which is twice in this case the atmospheric wind speed if it's the same in the two cases. And that explains why you require much more of the runway to come to a complete stop in the videos that we've seen than when you're landing in headwind. However, so the landing part is the harder part, but when you're flying, you really would like this more. You'd like a tailwind more because it's helping you, it's pushing you, it's giving you this free, free 50 kilometer per hour without having to pay for it with fuel or anything. Okay, so that is the relative velocity, and these are some manifestations of the relative velocity of the scooping example we have done, whether you're scooping from a pile of sand on the beach or you're scooping from a moving river. So now that we are familiar with the relative velocity, we're going to be analyzing systems that some of them can be moving. For instance, the nozzle on a garden hose, we would like to be able to analyze that. And for that, I may pick a control volume that is fixed in space. But in the case of an airplane, and I want to use a control volume analysis to do mass balance and force balance and energy balance to look at energy expenditures as well as lift and drag forces. Then I want to have my control volume to be moving at the same speed as the airplane itself, or in this case as the ship itself. So this is the second type of control volumes, is a control volume that moves at a constant speed. Here you had a fixed non-moving control volume, but in both cases you'll see that the shapes are the control volume doesn't deform. It's a rectangle, remains a rectangle all throughout the whole problem. But if you look at this, the engine head, a reciprocating piston cylinder engine head, you'll see that if you consider the air mass that's in the engine head, and you want to do mass and momentum and energy analysis on that, and you take a control volume that includes that mass of air, you'll see because of the compression action, the control volume itself is going to deform its shape in size and in shape. And that would be the more complex type of control volumes that we may come across in a deforming control volume that changes its shape with time. Because now all the boundaries can now be deformable, and you can see the relative velocities on the different boundaries can be different. So that increases the complexity of the problem. So these are the least complex, slightly more complex, and these can be quite complex problems to deal with when you have a deforming control volume. So now that we have defined control volumes, we didn't spend much time trying to explain control volumes, but because we've had our thermodynamic background and we've dealt with those quite a bit as mechanical engineers, now what we want to do is to go into our objective, which is to be able to write the conservation equations for a control volume, mass, momentum, and energy. And for that, we said you have here you have air going through your control volume, and in this case you have water on the water side, seawater in the case of the ship. So it comes in and then leaves from the other side. And if you try to follow a particle, it becomes a little bit too complex. So now that's where, from a dynamics point of view, that's where we need a theory to help us look at this time lapse movie of stuff coming in and stuff leaving, and try and look at it in a fixed sense. And that's what the Reynolds transport theorem helps us to do when we have a flux terms going into our system and leaving. So we're not going to cover it. You can read it in the book, and we're just going to jump right into the results to describe our energetics, mass conservation principle, as well as Newton's second law. So you can look at the Reynolds transport theorem in the book, and we're going to skip through it without loss of continuity. So the first principle we're going to look at and how to write is the conservation of mass for a control volume. So I thank you for your attention, and we will take it from this point in the next lecture.